So, this is the start of a new lecture, lecture 10, which is on Miller indices, planes and directions in crystals. So, in the previous lectures we understood the fundamentals of crystallography, the lattices, crystal systems, device lattices and symmetry and their correlations. Now, we will try to understand how you can quantify the crystals in terms of their directions and various phases, because this is the knowledge of this is very important to understand the correlation of anisotropic directional response of various properties in crystals. As you will see as a materials engineer later on in practice, that many of the properties of materials are very anisotropic. So, if you measure certain property along one direction, it is different than other directions. So, and this is true about mechanical properties, it is true about electrical properties, thermal properties and many other magnetic properties. So, to correlate the properties with directions, you need to have a method to quantify the crystals, directions and phases, and that is where this concept of Miller indices comes into picture. So, basically it is essential for completeness of crystal structures, and to be able to quantify the phases and directions in a crystal. And the reason for that is, let us say I draw a simple parallelepiped here. So, I have these atoms, okay. So, you can see that the separation between, so if it is a cube, then you know that this is A and this is A. You can see that the spacing between these atoms is A, but these atoms is not A, it is something else, it is let us say A by root 2. Spacing between this and this is different, spacing between, for example, this and this is different. So, given that different atoms have different spacings with respect to each other, the properties also change in different directions. So, if I measure some response in this direction, it is different from the response that is measured in this direction. Okay. So, that is why we need to understand what is this direction, what is this direction. Similarly, you can see that different faces of crystal has different atomic density. For example, this face has these 4 atoms located at certain distances. If I take this face, this has a different density, it again has same number of atoms, but it has different density. It will change when you go to FCC and BCC structures. For example, this face has different density, and as a result they will have different response, because they have different spacing of atoms between them, and they are packed differently in these directions. So, that is why it is necessary to evolve a system to quantify these things. Miller indices are in the name of a person called as William Hallow S. Miller, who coined the term, who came up with the system, and that is why these are called as Miller indices for crystallographic planes. Planes are nothing but the faces or facets of crystals. You can say facets of crystals. Okay. They are defined as So, this is to identify, they are defined as H, K, L for one plane in the single bracket, and if you have these brackets, they are not applicable to every crystal system, but it could be for a set of identical planes dependent upon on crystal structure, okay, whether it is cubic or whether it is tetragonal. So, you may not be able to write the same connotation for tetragonal if you are able to write the same for cubic. So, second thing is crystallographic directions. Crystallographic directions are various atomic directions. So, you can say atomic directions in crystal, and these are depicted as U, V and W. So, U, V and W in this bracket is a single direction, and if you write in this fashion U, V, W, then it is set of directions, and again just like planes, it is dependent upon the crystal structure. And here H, K, L and U, V, W all are integers. So, H, K, L are integers, U, V, W are integers. They can be written, there is no restriction on sign, it could be positive or negative. Similarly, this could also be positive and negative. Okay. So, they could be both positive and negative, but they are integers, they are not fractions. Okay. So, now let us first see the plane thing. Okay. So, planes in for a plane in a crystal, the equation which satisfied the plane in a crystal is H divided by A along x, x hat, and K divided by B, y, plus L divided by C to Z is equal to 1, where H by A is intercept on the intercept of the plane on of the plane. Okay. Similarly, H by B will be intercept on the y axis, L by C will be intercept on the z axis. Okay. And A, B, C are unit cell lengths or lattice parameters as we call them, and H, K, L are Miller indices. So, let us see following this definition. Let us say I have a parallelogram like this. Okay. Let us say this is the origin, and I define this as in some multiple of, let us say, A, 2A, 3A and 4A. Here I define as A, 2A and 3A, and here I define as, let us say, this is 8A So, this will be 4a, and I have, so this is 6a and this is 2a. So, I have a body which is something like that. And if I just connect these, so this is my plane. So, I can see my unit cell parameters are, so A is equal to 4a, okay, B is equal to 8a, and C is equal to 3a. All right. What are the fractional intercepts? So, fractional intercept along x is 2a by, this is along x, y it is 6a divided by 8a, and along z it is 3a divided by 3a. So, this is 1 over 2, this is 3 over 4, and this is 1. So, now you need to convert this into reciprocal. So, this is, now you take reciprocal. Reciprocal of this is 2, 4 by 3, and this is 1. But HKL has got to be integer. Okay. So, you need to convert this into a smallest set of integers. So, if you convert this in the smallest set of integers, what do you get? So, you get 6, 4 and 3. So, this plane is 6, 4, 3. That is how you determine the Miller indices of a given plane. So, let us do the same exercise for, let us say, this plane. So, if you do the same exercise for this plane, now for this, what is the fractional coordinate along x, fractional intercept along x? 1, 3a, 4a by, what is the fractional intercept along y? Infinity. What is the fractional intercept along z? It is parallel to z. This is z, this is y, so reciprocal is 1, 0, 0. So, this is h, this is k, this is l. This is 1, 0, 0 plane. Likewise, if you look at this plane, this is parallel to y and x directions, y and x axis. It has an intercept of 1 on z axis. So, this will be 0, 0, 1. Similarly, the one on the front will be, this will be 0, 1, 0. So, this is how you determine the crystallographic plane. So, basically the process is of determining a plane is, you define first a origin, okay, calculate the or determine the intercepts, take the reciprocal, and then convert to the smallest set of set of integers. Okay. Why smallest set of integers? Because if you look at 0 1 0 for example and 0 2 0, these are nothing but parallel planes. One is at the half spacing of the unit cell, another is at the full spacing of the unit cell. So, HKL and 2H 2K 2L 3H 3K 3L are basically same set of planes. They are parallel to each other, it is just that the spacing between them is different now. Okay. So, this is how you determine the planes. So, if I ask you now to do the reverse exercise, let us say I ask you to draw 1 2 3 plane. I draw a unit cell. Now, here choice of origin is very important. How you choose the origin, that is very important. Now, let us say conventionally I put this as x direction, this as y and this as positive z, positive x, positive y, positive z. So, I can see that now the key thing about a plane is that the plane has to be drawn within the unit cell itself. It cannot be drawn, it should not be drawn outside the unit cell. You can draw it, but it is not, that is not the purpose. The purpose is to draw all the planes within the same unit cell itself. So, if you have 1 2 3 plane, how do you choose the origin? You can see that H intercept is in positive x direction. When you do not have any negatives, negative is typically determined as, so if you have HKL, if you have negative sign, then it will be bar H, bar K, bar L. Okay. So, what it means is that if you have 1, then you are moving, your intercept is along the positive x direction. 2 means half the intercept is along the positive y direction, and 3 means 1/3 of the intercept along positive z direction. So, the origin which satisfied all the 3 directions is this origin. So, if I choose this as the origin O, then my intercept along x axis is 1. So, 1 2 3 should be, so you write 1 2 3, take the reciprocal, that is 1 over 1, 1 over 2 and 1 over 3. So, these are the reciprocals, okay, and then put them as an intercept in the unit cell. So, 1 is here, 2 is here and 3 is here. So, this is half, this is 1/3 and this is 1. Half, 1/3 and 1 is with respect to the lattice parameter. So, it is fraction of, so it is half of the B lattice parameter, 1/3 of the C lattice parameter, 1 time of the or equal to A lattice parameter 1 means. So, if I now connect these 3 points, this let me just complete this, this is half. Okay. So, this is the plane, let us say I define as A, B, C, this is the plane which is called as 1 2 3 plane. Okay. If you want to draw now, let us say, so just to get to you regarding 2 4 and 6, which is nothing but 2 into 1 2 3, you can see 2 4 6 will be parallel plane. Okay. So, 2 4 6 will be half intercept along x, quarter intercept along y and 1/6 intercept along z, and if you connect these 3 points, this will be 2 4 6. So, it is nothing but parallel, but the thing is that every successive 2 4 6 plane will be spaced closer as compared to every successive 1 2 3 plane. So, it is nothing but family of planes or set of planes which are parallel to each other. So, this is about the positive indices. Now, let us say I want to draw a plane which has a negative indices. So, I draw a unit cell. let us say I want to draw 1 bar 1 0 plane. Okay. So, I can see that HKL is 1 minus 1 0. The intercept is 1 minus 1 and infinity reciprocals. Okay. So, if I now look at it, I have k as minus 1, which means I need to choose a origin so that I am able to go minus 1 distance in the y direction. So, if I keep this as a origin, I can only go positive in x, positive in y and positive in z. However, if I keep this as a origin, if I shift my origin here, I can go in positive x, and if I go in that direction, I go in negative y, and this is important to be within the unit cell. So, if I do that, this is the intercept on x, this is the intercept on minus y, and there is no intercept on z, which means it is parallel to z, right, it is infinity. So, the plane would be this and that. So, this would be the one bar 1 0 plane. All right. So, you can do now the exercise at home as to. So, I will just now do one last exercise in this case. I draw a unit cell, just one last demonstration, and just to help you with how to find out the okay. Now, let us say I draw a random plane, let me choose one. So, I connect this point and this point. Is it a legitimate plane? Is a legitimate plane, yes or no? You have intercept along x, you have intercept along y, and you have intercept along z. So, how do you choose the origin now? So, you can see that the trick here is, let us say, so this is at half, right, this is at half. So, you can see that if you choose, this point is located at half of minus half x from here, this is located at minus half along x, minus half along y, and this is at plus along z. So, from this you can work out that this plane is, if I look at this, minus half and plus half. If you take the reciprocal, this becomes minus 2 plus 2, all this is nothing but minus 1 1. So, this is nothing but 1 bar 1 1. So, what is 1 bar 1 1 plane? Basically 1 bar 1 plane will be this and that. So, if I put these together, nothing but a parallel plane, but if you have to determine this red one, this one is a legitimate plane as well, you might have atoms sitting here. So, one way to do it is you do it in this fashion, or another way to do it could be to draw the parallel plane, so that you can choose a origin which is located on one of the corners, which means you have to draw the parallel planes, one more parallel plane, so that instead of ending in this fashion, it ends here. So, this will go out of the system. Okay. So, basically this line is parallel to that line. So, you can see that if you choose this as the origin, this is O prime, this is minus half y, this is minus half x, and this is plus half. So, this is how you can do. So, this line which is somewhere in between, which is not allowing you to choose the origin, draw a parallel line this, because these are parallel lines. Draw a parallel line. You can choose now this as origin. You can change this as a y z intercept, this is a x intercept, this is a y intercept, and then come to the same conclusion. So, this is something which is done, which you do to determine the planes. Another thing which you need to know about the planes is the spacing between the planes. For cubic system, spacing between the planes is given as DHKL is given as A divided by square root of h square plus k square plus L square, where A is the lattice parameter and h square plus k square HKL the mirror indices. So, you can see that if I go to the previous ones, you have these planes. So, this was one plane, this was another plane, you will have successive planes. So, what is the spacing between these planes? Or you can have, this is 1 0 0 plane, this is also this is 0 1 0 plane, this is also 0 1 0 plane. The spacing between these two is A. So, if you put that in, for 1 0 0 you will have D 1 0 0 will be equal to A, 1 1 0 D 1 1 0 will be equal to A divided by root 2, 1 1 1 D 1 1 1 will be equal to A divided by root 3. So, that is how you can determine the plane spacing, and you can also find that different planes are at different angles. Okay. So, for example, you can see that this is one bar 1 plane, and this is so you have one plane. Let me draw a different plane. You have one plane which is this plane, okay, and you have another plane which is this plane. If I want to calculate between the angle between the two of them, angle is given as cos theta is equal to h1 h2 plus k1 k2 plus l1 l2 divided by square root of h1 square plus k1 square plus l1 square into h2 square plus k2 square plus. This is called as interplanar angle. These are only for cubic systems, by the way. For tetragonal orthorhombic system the relations are different. In the next lecture we will now discuss the Miller indices for directions. Okay. So, we will stop here. This is only about the planes right now. Thank you.